There's a couple additional properties that we want to discuss. We can try to explain again using the shell model and the energies of the orbitals, looking at the periodic table. One property that we can talk about is something called successive ionization energies. The ionization energy that I introduced before is the so-called first ionization energy. That means I take an atom X in the gas phase and I add energy to it, presumably by having it absorb a photon, for example, and I make a positive ion, an ion with a charge of +1, and I give off an electron. That's the so-called first ionization energy. And it's also it's called just the ionization energy. But however, if I have this ion, again in the gas phase, and I hit it with another photon or add energy to it somehow and cause it to cause a second electron to be removed, then I'll make an ion with a charge of +2. And the energy that is needed to cause this to happen is the so-called second ionization energy. And in turn, if I take the atom with a charge of +2 and again in the gas phase, and I add energy to it, I will get, and to remove another electron, I'll get an ion with a charge of +3, and that's the so-called third ionization energy. And there could be a fourth ionization energy, fifth ionization energy, and so forth. Now, it's very instructive to look at these ionization different elements in the periodic table. It always, well, for one thing, so here's an element, sodium. There's the first ionization energy. Second ionization energy is higher. Well, for every single one of these, it always takes more energy to remove the second electron, and more energy to remove the third electron, and so forth. And that's simply because the electron is being removed from, it takes more energy to remove an electron from something that has a charge of +2 than from something that has a charge of +1. And similarly, so the ionization energies, the successive ionization energies always go up. However, it's instructive to look at how much they go up. So look for sodium, 496, and then the second ionization energy here, I2, is almost 10 times as big as the first ionization energy. Then we look at magnesium, 738 for the first one, 1451 for the second one. That seems like a reasonable, this is about twice as big. Then all of a sudden the third one is a lot bigger. So so it takes much more energy, many times more energy to remove the third electron for magnesium. Aluminum, I have some reasonable progression going here, 578, 1817, 2745, and then look, a huge jump to 11,000 something in kilojoules per mole to remove the fourth one. Well, what's the explanation for this? The explanation for this is simply that removing in magnesium, the first two electrons come from the valence shell, come from the last filled shell, and then the third electron has to come from an inner shell, and that takes a lot more energy. For sodium, the first electron comes from the 3s shell, and now the 3s shell is empty, and the second electron comes from the 2 shell, and it takes a lot more energy to do that because remember those orbitals are much lower in energy. So that's marked on this table with this dashed line, and notice that separates removing valence electrons from removing inner shell electrons. And notice that all across here, for all these elements, there is a big jump when I have to remove an inner shell electron. Again, this is more evidence for this particular shell model of the atom, and it's explained by the atomic orbital energies that I showed earlier. There's another property that you can think of as being the opposite of ionization energy, and that's the so-called electron affinities. For electron affinities, we're talking about what the propensity of a neutral atom, again in the gas phase, X, to take on an electron instead of giving up an electron. And we want to look at the energy change for this. Well, recall that the energy changes, all the ionization energies are positive. It always takes energy to remove an electron. However, so ionization energy is always positive. That's what I just said. But electron affinity can be positive or negative. Adding electron could be an exothermic process. Well, the trend is sort of the opposite of ionization energies. You can think of it, this is sort of the opposite process. At the right-hand side of the periodic table, before I get to the noble gases, electron affinities are the most negative. And that's because these atoms are those that attract electrons. And that's simply associated, again, with the energy of the highest orbital, which is lower on the right-hand side of the periodic table. Again, look at the graph I introduced earlier, showing the orbital energies as a function of atomic number. So on the left-hand side of the table, atoms tend to give up electrons. On the right-hand side of the table, atoms tend to attract electrons. So here you can see that in general. It's a general trend. It's not absolute, and I'm not going to go into various explanations for the glitches here, but notice that electron affinity becomes more exothermic as you go from left to right across the row. Lithium is -60, and fluorine is -328. The noble gases, noble gases don't take on extra electrons. And it's a rare enough process, so it's probably not even measured. But at any rate, it takes a lot of energy to add an electron to neon, because neon already has filled shell, as do all the other noble gases. But the overall trend for any of these, notice more exothermic or more negative as I go from the left-hand side of the periodic table to the right-hand side. Again, we're just looking at the overall trend, not at all the various glitches here.